Good morning, good afternoon, and good evening, everyone. My name is Maxim Chepelev. I'm an economist with the GTAP Center. And today we're delighted to have Dominique van der Merwe, Director of the Center for Global Trade Analysis, presenting at this GTAP webinar series. He will be presenting a paper entitled Latin Hypercube Sampling Utility with an application to an integrated assessment model. This work has been recently published in the Journal of Global Economic Analysis in the previous issue. So there is a link at the webinar, and you can locate the paper. Everything is freely and publicly available, all the replication codes, so you can download everything and explore in more detail. So in this paper, as you will see later in this presentation, Dominique is developing a utility that creates a Latin Hypercube sample that allows to sample essentially a wide range of different parameters from their Monte Carlo, replicating essentially the Monte Carlo sampling strategy. Some of you might be familiar with Gaussian quadratures that are used in their sensitivity, systematic sensitivity analysis in their GTAP utility. So these applications that Dominique would be presenting is somewhat similar, but more universal. And just before giving the floor to Dominique, to remind you a bit on the logistics. So we will have a 25 minutes presentation, which will be followed by discussion. Feel free to post your comments during the presentation to their comment box, or you can also raise your hand after the presentation during the discussion part and ask your question directly. And at this point, without further ado, I will give floor to Dominique.
Thank you, Maxim, and welcome everybody to this GTAP virtual seminar. In the CGE world, we don't often do much with kind of Monte Carlo type simulations. There's a good reason for that. It's very costly in terms of computer times, but I think we're approaching a point now where the computers are improving as well as the software, and that we could think about doing more systematic Monte Carlo type simulations, even with relatively large CG models. So I'm going to introduce today a utility that I have developed from another one that generates what's called a Latin Hypercube sample, which can be used as one strategy for Monte Carlo simulations. All right, let's see if we can advance. We did. Okay. There are 4 parts to this presentation, so I'm going to introduce a little bit first what Latin Hypercube sampling is, the strategy for this type of sampling. Then I'm going to show an application to a specific integrated assessment model, but really this strategy can be used for sampling any set of uncertain parameters. I'll show a few of the results from the integrated assessment model, and then I'll conclude. So what is Latin Hypercube sampling? I might use LHS, a little bit quicker to say. It's a stratified form of Monte Carlo sampling. So and I'll explain that in more detail in the next slide. So the idea here is to reduce the sample size. So you don't, in a standard kind of Monte Carlo simulation, you need to sample a huge number of observations. Here, you can reduce that size. There's a specific strategy for doing that, but also covering the entire sampling domain. The other really critical part of this utility is that you can target correlations across 2 or more of the variables you're sampling. This is particularly relevant in climate change, because for many of the parameters in the climate modules, we do know what the correlations are across the parameters. So it's really important make sure that you're controlling for those correlations when you're doing your sampling. The current tool is coded in C, C++. It comes as an executable. It's really simple to use. In principle, I think it could be embedded in R using some of the tools that R has. I haven't done that yet. I haven't really seen the need to do it, but it can be done. It comes from an original Fortran program that was developed at Sandia Labs back in the 1990s. And you can certainly look at the original documentation for this. I've added quite a number of additional probability distribution functions to the ones that were already in the original. Many of them are these extreme distributions that are used a lot in economics, such as the gumball, for example. And then I've also added a lot of output options because the original was not all that useful for many of the software tools that we use, but now there are a number of other options. Some of you may be familiar with Excel's at-risk add-in. It's quite popular. It's certainly in the business schools and things like this, but the at-risk requires you have to pay for at-risk. To be honest, I don't know how much it costs, but Excel, I just find it to be a terrible tool for doing the type of modeling that we do. So I would not encourage people to use at-risk unless they really need to. All right. So what's the sampling strategy? Well, the key sampling strategy is what's called the inverse transform method. So if you have a cumulative distribution function, CDF, and it's invertible, then the way you sample is that you sample from the uniform distribution. So that's on the 0, 1 range. And that gives you a certain probability, and then you can stick this into your inverse function. So here we have the example of the logistic CDF. So it's the top equation, all right? And you can invert that quite readily in terms of the probability distribution, so that the quantile function is that simple second equation, mu plus s times the log of the probability over 1 minus the probability. So you sample, if you look at the graph there, you sample on the uniform distribution. That's the y-axis. So you're sampling on between 0 and 1, and then using that inverse function, you can get your sample random deviate. So if you look at the top line there, it's roughly 90%, 0.9 is a probability. And with the parameterization of this logistic distribution, that leads to a random deviate of around 17.5. All right, so you can do that n number of times, and you can map out then your entire distribution function. So that's the key to sampling. If you don't have an easily invertible distribution function, you have to use other numerical methods to invert the distribution function. So what LHS does, it's a stratified sample, and that means that you cut the interval that you're looking at. So if you're sampling n times, you're going to cut the interval into 1 over n. All right. So if you want 100 observations, you're going to cut your interval 0 to 1 into 100 different ranges, and then you sample from each of those subranges. So the advantage of that strategy is that you're guaranteed to cover the entire range of your CDF. All right. And just to give you some intuition from here, on the graphs here, we're looking at different sample sizes going from 50 to 5,000 in steps of 50. All right, And you can see when you have very low sample sizes, less than 1,000, all right, your sample distribution is far from your anticipated distribution. So on the left-hand side panel there, you have the mean. The expected mean for this distribution is 0. And you can see when you do just standard Monte Carlo sampling, the mean at the beginning is very high, 1.5 or over 0.5. And it's much closer when you're doing the LHS sampling for the small sample size, but there's still some deviation. But you can see that with the LHS sampling, you very quickly converge towards the expected mean of the distribution. But even with Monte Carlo sampling, you still have deviations, even when you're sampling 3,000 observations. So it does settle down when you get to 4,000 and 5,000 and beyond. For the variance, the standard deviation, the deviations still are pretty substantial for the standard Monte Carlo sampling compared to the LHS sample, which pretty quickly converges towards the anticipated standard deviation. So that's kind of the motivation behind the LHS sampling. The utility is a compiled program, so it's very easy to integrate into a workflow. It uses very standard C and C++, so it would be even for those of you working in a Linux environment or a Mac OS environment, it compiles in a very straightforward fashion. We have now 5 output options, so CSV, XML. XML is something that can be loaded into Excel very just as readily as an XLS file. A standard GAMS file or a GDX container, and then I still have backward compatibility with the original output option. We also have code that will facilitate the reading of the CSV file for those of you who are using GTAP, so it's easy to integrate into the GTAP environment as well. There are around 40 distributions right now. Most of them are continuous. We have all the kind of standard ones, normal and all of its variants. We have Frechet, Gumbel, some of the extreme, and then there are a bunch of other ones. There are also discrete distributions. And the utility also allows the user to specify correlations across the deviates. The default is 0. So when you're sampling, just the correlation matrix is just the identity matrix. So that's the utility. I'll show the sample input file a little bit later. So let me move on to the integrated assessment. I think many of you are familiar with what integrated assessment is. So you have this kind of circular diagram here. So you have your economic model. That's the top rectangle, where you have production, demand, energy, land use. All right. This could be a CG model, but it could be some other economic model as well. This leads to greenhouse gas emissions and potentially other environmental indicators. And these may be influenced by various different projections. In the climate change community, many are using the shared socioeconomic pathways for demographics and GDP growth. And then you might have assumptions on technology, such as improvements in energy efficiency, et cetera. The emissions go into the atmosphere, and that then goes into a climate model, which generates one or more climate signals. We're going to focus here on temperature, but could be precipitation, and there are all sorts of other potential indicators that may come out of a climate model, such as extreme events, etc. And then the temperature signal or the climate signals have impacts, biophysical impacts or economic impacts. For example, rising temperatures may impact on crop yields, on labor productivity, and a host of other indicators, and they feed back into your socioeconomic model. This is why it's called integrated assessment. And there are policies both on adaptation and mitigation, which may influence that final link between impacts and the socioeconomic model. So I'm going to talk a little bit about the META 21 model. This came out in 2021. The paper is by Dietz et al. Very interesting paper. It's focused mainly on biophysical tipping points. For those of you familiar with IAMs, it's kind of like a dice model with these tipping points. So the economics is very simple, but that's not really the focus of this talk. It's using a relatively new simple climate model called FAIR. For those of you following DICE, Nordhaus's latest adaptation of DICE is also using the FAIR simple climate model. I'll talk a little bit about that in a couple of slides. One of the interesting features is that they do downscale the change in global mean temperature down to the country level. So they're looking at country-specific impacts caused by changing temperatures, including sea level rise and non-market damages. The model captures changes in the planet's albedos from the change of ice cover. So that also impacts the change in the global mean surface temperature, raises it somewhat from a model that doesn't include the impacts of albedo. One of the most interesting features is they also have interaction effects across the tipping point. So one of the tipping points, for example, is the Amazon dieback, and that may impact, for example, the sea level rise through the Antarctic ice sheet. So they captured these interactions effects as well. The original version of the model was in Excel. I have a GAMS version of it, which replicates the Excel, and I believe the current authors are moving that model now to the MIMI framework from Berkeley University. What are the tipping points that are included? There are 7 of them. So the thawing of the permafrost, this is carbon and methane that is captured in soils, relatively shallow soils, and warming temperatures will lead to their release. Same with the dissolution of methane hydrates. These are methane bubbles captured in the oceans. Again, they may be released through temperature impacts. The Amazon dieback is going to lead to a jump in carbon emissions. Ice sheet melting will lead to sea level rise, and they have 4 sources of this: thermal expansion, small ice sheets and glaciers, the Greenland ice sheet, and the West Antarctic ice sheet. The 6th one is the change in the deep underwater currents, also known as the Atlantic meridional overturning circulation, or the thermohaline circulation. That can affect changing temperatures at the country level. And then the final one is the weakening of the Indian summer monsoon. I'm only going to focus on 2 parts of the META 21 model. I'm going to focus on the energy balance module, which determines the change in temperature, and on the dissolution of methane hydrates. So the energy balance model has a very relatively simple mathematical form. It's just an algebraic equation. So temperature in time t is a function of what temperature was in time t minus 1, plus you get this impulse from radiative forcing. You could think of that as essentially coming from changing emissions. All right, so the emissions change the radiative forcing, which then will change the temperature. So even if there's no change in radiative forcing, with this type of model, you're still going to get inertia in the system, which is going to lead to rising temperatures over time, even in the absence of changes in radiative forcing. Don't worry so much about the parameterization. So these are the parameters that we're going to sample. Basically, this A matrix is the one that moves energy from one box to another. And so in the most elaborate formulation of the EBM, there are 3 boxes. So there's the atmosphere, and then the shallow and the deep oceans. In the original DICE model, it was only 2 boxes. So it was atmosphere and shallow ocean and the deep ocean. With the new FAIR model, they've added, they've split the atmosphere and shallow ocean boxes into 2 separate boxes. And this has enabled them to much better capture the change in temperature compared to the very large climate model. So the very large climate models are much more detailed, obviously, but you know the most elaborate of them takes six months to run. Here, with this simple model, it takes only half a second on the computer. So it's a very succinct way of getting your global change in temperature. So here are the sampling assumptions. All right, so for the different parameters, again, I'm not going to go into too much detail, but you can see that it's a mixture. So 2 of the parameters are Pareto, one parameter is triangular distribution, and then 2 others are normal distributions. And you can see with the default parameterization, what are the expected means and standard deviation. And we're sampling this 10,000 times, and you can see that the sample is spot on. There's absolutely no deviation in the sample from the expected mean and standard deviation. All right. We do impose, however, a correlation across the different parameters. So the top table here are the correlations for these 5 parameters. All right. These are the ones that have been econometrically estimated or statistically estimated from the large climate models. All right. And then the second table is the correlations as derived from the sample itself. And you can see that there are some pretty significant deviations. So if you take a look at the first column with the 3rd row, so that would be chi1 and chi3, and you can see that we anticipated a correlation of minus 4.4, 0.44, and the actual one is 0.34. So that, in percentage terms, that's quite a large deviation. In absolute terms, it's not that large. And overall, I'd say the fit isn't that bad, and it's not going to improve dramatically with a greater sample size because there are restrictions on the correlation. When you have more than 2 random variables, there are restrictions on how free these correlations are. So sample size is not necessarily going to lead to a significant improvement. All right, the other thing I wanted to point out are the tipping points. And the tipping points are also sampled, but they're sampled every period, where because they depend on state variables. So the equation here is the probability of the ocean methane hydrates starting to be released into the atmosphere. And that probability is in the form of a hazard function. So it's 1 minus the exponent of minus b times the temperature. All right. So b is the hazard rate. And as temperature rises, the probability of that of the ocean methane hydrates being released into the atmosphere increases. All right. So the model has an indicator function, and so as long as we don't have a positive, the event actually occurring, the indicator is 0. All right, but once you sample using this random binomial sampling mechanism, so this is just between every period, you just calculate the probability, so that's that p, and then you just do a sample based on that p of the random binomial. So that's a probability of the event occurring or not. And here you can see on the graph, first of all, the red line is the probability itself. And as you can see, the probability is relatively low at low temperatures, but at 3 degrees C, the probability of the ocean methane hydrates being released is almost 1/3. So when you sample one time out of 3, you're going to expect it to have occurred. But actually, the mode of this distribution is around 0.8 degrees, as you can see. So that's when the ocean methane hydrates would start being released on average, would be when temperature reaches 0.8. You cannot model this explicitly if you're thinking about modeling this strategy in GAMS or in GTAP. You would have to do it between periods because so there'd be a lag, because that random binomial function is not cannot be part of a model. You can't sample while you're actually running the model. So it would have to be done between periods in the recursive dynamic framework. Here's a snippet of the input file. So the output file, I'm going to ask for a GDX. Again, you can ask for 1 to 5 output options. You can set the seed and then set the number of observation. You can also have more than one replication. Here, we're just going to ask for 1. But if you ask for more than 1, you can reseed it and restart the entire simulations with a different set of random deviates. Then here you provide the name of the parameters that you're going to sample and their distribution and the parameterization of the distribution. And then finally, we have the correlation matrix that is provided for each of the parameter pairs. Okay. Let's go to a few of the results. So here's the distribution of the social cost of carbon in terms of a Fox and whisker plot. You can see that a very large majority of the sample with tipping points is going to be roughly between $40 and $100. If you exclude the tipping points, it's a little bit less than 40 and under around $80. So obviously, the tipping points raises on average the social cost of carbon and the range of it as well. So with the tipping points in this model, the social cost of carbon would be $60, and without it, it's $48. For those of you who follow this literature, the U.S. had been using for many years a level of around $44. So that that the Meta 21 model is pretty consistent with the original version of the social cost of carbon from the U.S. government. It is currently revising the social cost of carbon and is coming up with much larger values, largely because it's using a much lower discount rate. All right, so the other thing you can see from this chart is that there are quite a number of outliers as well, all the way up to $500 under certain configurations. This chart shows the potential range of change in temperature between now and 2200. So the curves on the outside are the min and the max, and the dark purple area is the 95% range for the temperature change. So obviously, with tipping points, the range is much larger. The maximum all the way up to 10 degrees Celsius by 2200, where it's under 8 degrees for the version of the model without tipping points. And the confidence intervals are also tighter without the tipping points. Not very surprising there. The last thing I wanted to show you was the avoided damages. So this is when we exclude the tipping points. So this is compared to the scenario where we have the full damage scenario with all the tipping points. All right. So the tipping points are on average, I'd say, decreasing per capita consumption by roughly around 2%. All right. There is, I think, only one outlier. It's a little bit hard to see on this one, but it's the Netherlands, where the tipping point leads to a decline in consumption of about 10%, and that's largely, obviously, from sea level rise. The Netherlands would be the most impacted by that. And then on the other extreme, some of the Central Asian countries would actually benefit from the tipping points. So that's an interesting counter case. Okay, so just a few concluding remarks then. So the LHS utility generates a stratified sample from Monte Carlo simulation. So that leads to a pretty tight sampling strategy, but it also includes, and I think this is critical for much of our work, specific assumptions on correlations. We have published a user guide that you can find in the GTAP working paper series. I also did this work using parallelization, which is actually pretty easy to do, even on our desktops. It's something that can lead to very significant savings of time. So for this Meta 21 work, for example, where I sampled 10,000 times, and you have to run the model twice, one without the tipping points and one with the tipping points. Without the parallelization, it took about 6 hours, and with parallelization, it took 30 minutes. And we've been experimenting with this parallelization for some of our work here at the center as well. I described how to do this in a different working paper that you can also find in the GTAP working paper series. Very, very simple to implement. As Maxim said in his intro, a lot of people have been using Gaussian quadrature to look at sensitivity, and it can be very useful in some contexts, but as soon as you're working with a large set of uncertain parameters, it becomes relatively difficult to work with. And there's some evidence that it's not particularly good at trying to target higher order moments such as skewness. So those higher order moments are automatically captured in any kind of Monte Carlo type strategy. And the other thing I want to say is that a lot of these impacts that are in Mega 21, especially the tipping points, can readily be incorporated in any CG model that generates greenhouse gas emissions. So even though the economic part of Meta 21 is very, very simple, a lot of the apparatus that is constructed around the economic emissions model can easily be ported to other models, and the final reference is to the journal article itself. So you can here's a short list of the references from this talk. So I think that's it. We're open to questions and suggestions.
Thank you, Dominic. I do not see any questions in the chat, so if anyone has any questions or comments, feel free to raise your hand and then just unmute and talk. Maybe while we are waiting for questions, I have one. So I was wondering if you have any ideas on how this work can be used, considering the current kind of scope of work of the center. How do you see it, in maybe future projects or in some current projects, how it can enhance their approach that we are currently using?
Well, certainly any work we do on climate change, I think, given the uncertainties both in the climate system and in the potential impacts climate's going to have on the socioeconomic system, I think I think using these approaches is really critical. I've done it in different contexts as well. I mean, you could, we do, well, think about the work we're currently doing on food security and diets and things like that. There's a lot of uncertainty about how crop yields are going to change with or without climate change. So you could imagine adopting this type of uncertainty analysis in that context as well. So, yeah, I mean, I think there are boundless areas where this may be useful.
Any other questions, comments, maybe follow-up thoughts? Maybe someone has been using similar techniques in their work and has some thoughts to share.
Right. Well, I think if there's nobody at the last minute, I think we can call it a day.
Okay. Yeah. If there are no questions, yeah. Thank you, Dominic, again for really insightful presentation. And just to remind everyone, there is a paper published in the Journal of Global Economic Analysis. So if you would have any clarifying questions or points, feel free to go to that paper. Everything is publicly available. You can download the model code and the code for the sampling technique, and also meta model code, so you can replicate everything. And Ginger has just posted in the chat the link to the paper, so feel free to explore it. Yeah.
And
okay.
Please provide us feedback if you do decide to use the tool.
Okay, great. Thanks, everyone, and hope to see you again maybe in the next virtual seminar and GTAP conference. Thank you.